Welcome to Brain Vision.
Hi everybody, so what we have is a stream of steam at 80 psi and 400 degrees F. It's going to be 1. And we have a stream of water that's at 80 psi and 60 degrees F. That's going to be 2. That's mixed in an adiabatic device such that the mass flow rate of the steam is 0.05 pound mass per second and the mass flow rate of water is 1 pound mass per second. What we're asked to find is the outlet temperature after mixing if we know the exit pressure is 80 psia. So the first thing we're going to do is write down our assumptions. So we're going to assume that this is operating at steady state conditions, so nothing will be changing with time. Next, we're going to assume that all changes in potential energy, all changes in kinetic energy, as well as any heat and any work is all negligible. And we're also going to assume that there's no heat transfer going on between the mixing device and the surroundings. So what we're going to say that Q sir is equal to 0. Now what we're going to do is we're going to take the mixing device as our system and we're going to do our energy balance. So what we're going to say is that the total energy coming in minus the total energy leaving is equal to the total change in energy of the system. Now as we stated before, we're operating at steady state, so the total change in system energy is going to be equal to 0. Therefore we can say that E dot in is equal to E dot out. Now we can expand upon these terms and say that E dot in is equal to M dot 1 H1 plus M dot 2 H2, and that's going to be equal to the mixture coming out. That's going to be M dot 3 H3. Now from just doing a simple mass balance, we'll know that the mass flow rate of the mixture exiting is equal to the mass flow rate of the incoming steam and the incoming water. So that's just going to be equal to 1.05 pound mass per second. Now what we can do is look at our incoming properties and determine what our enthalpies are. So we know the incoming pressure of the steam is 80 psi, and we know that it's at a temperature equal to 400 degrees F. Now this corresponds to an enthalpy that's equal to 1230.8 BTU per pound mass. And if we look at our incoming liquid water, that's at a pressure of again 80 psi, but at a temperature equal to 60 degrees F. Now this corresponds to an enthalpy equal to 28.08 BTU per pound mass. And now these values are just coming from our thermodynamic tables. So now what we can do is rearrange that energy balance that we had above and solve for H3. So we know that H3 will just be equal to M dot 1 H1 plus M dot 2 H2 all over M dot 3. So we're plugging in for all these quantities. We get final enthalpy equal to 85.35 BTU per pound mass. Now what we can do is define our exit state. Our exit state is going to be defined by the pressure and this enthalpy. So we can say that at the state 3 at our exit, our pressure is equal to 80 psi, and our exit enthalpy is equal to 85.35 BTU per pound mass. Now, as we did with determining our entering enthalpy properties, we can use this state at position 3 to determine the temperature. And what we see is that when we look up this pressure and this enthalpy in our table, we'll find that this corresponds to a temperature equal to 117.3 degrees Fahrenheit. And that is the final mixture temperature, and that's our final answer.